What's up, easy peasy OChemers? Welcome back to the channel. In this video, we're going to look at how we can break open epoxides in both acidic and basic conditions. So as I kind of just gave away, epoxides can be broken in both acidic and basic conditions. Now it's really important that you know that the condition you're in will determine which carbon in the epoxide the nucleophile will attack. If you're in acidic conditions, aka if you have an acid like sulfuric acid, phosphoric acid present, the nucleophile will attack the more substituted carbon in the epoxide. We'll talk more about why this is the case in just a second, but for now, just know that the nucleophile attacks the more substituted side when you're in acidic conditions. If you're in basic conditions, the nucleophile will attack the less substituted carbon in the epoxide. Now, in addition to determining which carbon the nucleophile attacks, the condition you're in will also determine what nucleophiles you'll see being used to break open the epoxide. In acidic conditions, you'll see weak nucleophiles being used. And here's the reason why. Strong nucleophiles tend to be strong bases, and weak nucleophiles tend to be weak bases. We want to use weak nucleophiles in acidic conditions because, again, weak nucleophiles tend to be weak bases. This means that they won't get protonated as easily by the acid. If we use stronger nucleophiles, which, as we just discussed, corresponds to being stronger bases, then the acid in the solution would just end up protonating the nucleophile instead of carrying out its proper role in the reaction. In basic conditions, we see strong nucleophiles being used to break open the epoxides. So as we just discussed, strong nucleophiles are typically strong bases, and weak nucleophiles are typically weak bases. And so, for those of you wondering what makes basic conditions basic, it's the presence of these strong basic nucleophiles in the absence of acid that makes basic conditions basic. Now, here's a visual highlighting the key points of everything we've discussed so far. So in acidic conditions, which again means in the presence of an acid like sulfuric acid, phosphoric acid, etc., one of these weak nucleophiles will attack the more substituted carbon in the epoxide. And in basic conditions, one of these stronger nucleophiles will attack the least substituted carbon in the epoxide. Now here's what we should expect our products to look like in acidic and basic conditions. In acidic conditions, the top row, you should get your weak nucleophile on the more substituted carbon and a hydroxyl group on the other carbon. In basic conditions, the bottom row, you should get your strong nucleophile on the less substituted carbon and a hydroxyl group on the more substituted carbon. Now let's take a look at the mechanism for breaking open an epoxide under acidic conditions with water as our nucleophile and sulfuric acid being our acid. So looking at the top row, we see sulfuric acid written above the arrow. As we know, oxygen is much more electronegative than hydrogen, and this difference in electronegativity means that oxygen will pull the electrons in hydrogen towards itself, causing a partial positive charge to form on hydrogen. Now take a look at our epoxide on the left-hand side. We have an oxygen bound to two carbons. As we know, oxygen is more electronegative than carbon, so we get a partial negative charge forming on oxygen. Now opposites attract, so this partial negative charge on oxygen in the epoxide will be attracted to the partial positive charge on hydrogen in sulfuric acid, and the oxygen in the epoxide ends up getting protonated. Now take a look at the bottom left corner. We see our main product from the previous step written again. Notice that oxygen now has a positive charge. This is bad. Remember, oxygen is an electronegative atom, meaning that it likes to have negative charges, not positive charges. So, oxygen becomes sad and it will do whatever it can to fix the problem. And what it will do is it will start to pull away from the more substituted carbon in the epoxide, causing the carbon-oxygen bond to stretch and become weaker. Now bonds contain electrons, and the electrons in the bond being stretched are moving farther and farther away from carbon. This causes a slight positive charge to start forming on carbon. Now, some of you may be wondering, why does the oxygen pull away from the more substituted carbon and not the other carbon? And the answer to this question has to do with the stability of the positive charge. As we know, tertiary carbocations are much more stable than secondary or primary carbocations. Now, this positive charge that is forming isn't a carbocation, but like carbocations, it is more stable on more highly substituted carbons. So, oxygen will pull away from the carbon that will produce a more stable positive charge. So, as we just discussed, the protonated oxygen in the epoxide is unhappy, and in an effort to get rid of its positive charge, it starts pulling away from the more substituted carbon. This causes a slight positive charge to form. Now remember, we also have water in our solution, and as we know, oxygen is much more electronegative than hydrogen, so we get a partial negative charge on oxygen. Now opposites attract, so water ends up attacking the electrophilic carbon, causing the epoxide to break open. Now take a look at the bottom left corner. We have the product from the previous step redrawn. Notice that the oxygen from the water that just attacked now has a positive charge on it. This makes oxygen sad because oxygen likes negative charges, not positive charges. So it begs for someone to come and help it. And thankfully, the conjugate base of sulfuric acid is there to the rescue. And what will happen is the base will end up snatching a proton from the positively charged oxygen, making oxygen happy again and giving us our final products. Now let's take a look at the mechanism for basic conditions with hydroxide being our nucleophile. So in the top left corner we have our epoxide, and in it we have an oxygen bound to 2 carbons. Because oxygen is more electronegative than carbon, we get partial positive charges forming on the carbons. Now hydroxide is our nucleophile, and with its negative charge it's going to be attracted to these positively charged carbons. But the question becomes, which carbon will it end up attacking, and why? It turns out that in basic conditions, the hydroxide will attack the least substituted carbon, because this is the carbon with less steric hindrance. Now to remind you, the reason why in acidic conditions the nucleophile attacked the more substituted carbon is because the oxygen, once it was protonated by the acid, pulled away, making a much more electron-poor carbon and an easier to break carbon-oxygen bond. Thus in those conditions, it was much more favorable for the nucleophile to attack the more substituted carbon. But here we don't have that oxygen pulling away, so the nucleophile attacks the less substituted carbon. Now take a look at the bottom left corner. We have the product from the previous step rewritten. Now before I tell you what's going to happen, I just want to take a moment to clarify where the water you see above the arrow came from. So remember, whenever we do reactions, we typically do it in a solvent. Water here is the solvent, and it's going to play a role in the reaction. For epoxide opening in basic conditions, you'll typically see water or alcohols used as a solvent, and know that they will often have a role in the reaction as you're about to see. So in water, oxygen is bound to 2 hydrogens, and as we know, oxygen is much more electronegative than hydrogen. This causes a partial negative charge to form on oxygen and a partial positive charge to form on hydrogen. Now, if you take a look at the oxygen from the broken epoxide, you'll see that it's not protonated and has a negative charge on it. Opposites attract, and the negatively charged oxygen will snatch a proton from the water, giving us the final product you see on the right-hand side. And that, my friends, is a wrap for this video. If you want some practice problems or you want to see how stereochemistry plays a role in opening epoxides, check out the video suggested above. And with that, great job everybody!